Okay, guys, there's good news. 9.5 is the last official section that we will be doing this year. I'm not saying we're not going to learn anything else that you've never learned, but as far as progressing through the book, 9.5 is it. So we are about ready to have a test on polar and parametric. We'll talk more about dates in class. So last video we talked about polar graphs and then polar slope. Today we're going to talk about polar area and arc length, which is just two more natural questions that you might want to ask about a polar curve. So let's start with a little bit of calculator stuff. If you change your mode to polar, your y equals button will look like this, where we are, y and x are now r and theta. We talked about how that's just a different system for locating, and it creates a bunch of interesting graphs. 8 sine 2 theta. Here's what that one looks like. And one of the issues with polar is going to be what domain of theta values graphs out what portion of the graph. Usually your graph will automatically be set from 0 to 2 pi. Let's just take a look, play around a little bit, and see what happens if we graph it from 0 to pi. We get those first two leaves of this flower, or whatever you want to call it. If you go from 0 to pi over 2, we should just get one of those petals. A lot of times they're called petals. The question will say find the area of one petal, and so on and so forth. Back to standard would have been 2 pi to graph the full thing. You can see the petals get traced out in a certain order, and then it stops. And then if we were to make it 4 pi, then it's just going to retrace itself 2 times. So kind of watch closely as it graphs. It's graphing once, and now it's graphing again, and then it stops. So some of the questions will say find the values of theta that will trace it just once, and a lot of that's just going to be guess and check on the calculator. So let's talk about polar area. Let's change, by the way, on your zoom, anytime your zoom is messed up and you want to get back to normal, you can go to zoom 6 for zoom standard. I like to then go to zoom 5 for me, which is zoom square, which doesn't distort my picture, because we have a rectangular screen. So if you do -10 and to 10 in both directions, it'll be distorted because of the difference in the length and width of your screen. So zoom square will do that. Anyway, back to window. Let's look at just the first quadrant. So let's go from 0 to about, well, let's go 0 to 15 and y from 0 to 10. That should keep it square, I think. I can get better than that. Let's go. Let's go out to 8 is my kind of radius. So I'll just go to 9 in both directions. I'll lose my squareness, but that's all right. So here is one petal of this flower. So let's talk about, by the way, this is what gets traced when I go from 0 to pi over 2. All right, so that's my, when my direction is 0 all the way till my direction is pi over 2. Now, remember, when you did integration, when you learned about integration, what's going on with an integral of a function f of x is you are starting at a point A and finishing at a point B, and at every point, basically, you're creating a little rectangle. And you're letting those rectangles get infinitely thin, and using the limit process. That's not today's topic, but just to refresh your memory, we get the exact area. So this area would be the integral of f of x with respect to x from a to b. So I just want to refresh your memory on that to bring up some connections between that and polar area. When we do polar area, what we're doing is as your graph proceeds around this way, just like when f of x proceeded from left to right, instead of dividing it up into little rectangles that become infinitely thin, we're going to divide it up into little triangles sort of like pieces of pie, like this. They're not going to have the curvy edges like a piece of pie would, but we're going to do little triangles like that. And as they get infinitely thin, this error space up here will go away in the same way that my error over here went away as my rectangles got infinitely thin. So this is the basis of polar area. You're not going to need to do difficult math steps technically in finding this. I just want you to understand the basis, that it's doing a similar thing just with triangles instead of rectangles. So what that's all going to do, and I'm sure if you wanted a nice weekend, you could Google it and see where all this came from. But this leads us to our polar area formula. We'll just kind of cut to the chase. This is from 9.5 in your book, page 694. If f is continuous and non-negative on the interval alpha to beta, how my pen got so... which are just sort of angle versions of A to B, because we're dealing with angles now instead of XY points, then the area that's generated is going to equal this. 1/2 integral from alpha to beta of f of theta, which is just your polar function, squared d theta. And again, you don't need to be concerned with where that came from. Just realize that if you want to find the area of a part of a polar graph, integrate it between whatever two angles. An old integral, I would say, what's the area between A and B? Now I'm going to say, what's the area between alpha and beta? Because instead of A and B, I have alpha and beta, whatever those angles are. And just plug into this formula. All right, you're going to have your function squared, integrate it, multiply it by 1/2. This is actually a pretty easy formula, and the use of it's not going to be that bad. A lot of times it's just going to be a calculator, and a lot of times it'll be stuff you can integrate fairly easily. So let's get an example. Actually, let's find the area of this right here. Let me get rid of that ink, get it out of the way. So remember, my polar equation was 8 sine of 2 theta. And also remember, this is kind of sometimes the trickiest part, is finding the alpha and beta, because the question will say, find the area of one of the petals. So let me get my window back to normal. Finding the area of one of the petals requires you to know what alpha and beta are. So you can kind of play around with the window and see. If I start at 0, and I've already done this, and go to pi over 2, that's going to trace one petal, so that you're accumulating area as you move around, just like you accumulate area as you move left to right on the graph. If I say move from A to B, you're like little skinny rectangles all the way across until you get your full area. Well, the same thing's happening on here. So you're getting your area, you get little triangles of area all the way around from 0 to pi over 2. And I think because the graph kind of starts in there tight and then moves out and then comes back in, sometimes it's hard to imagine those little triangles that you're adding up, but that's where the calculator is going to come into play. If 0 to pi over 2 is what graphs it, then 0 to pi over 2 is the limits you want to use in your integral. So anyway, back to what I was saying. 8 sine of 2 theta. So a typical question would be something like this. Find the area of one petal of r equals 8 sine of 2 theta. All right, so that's not so bad. And the calculator lets us figure out that one petal is going to be generated from 0 to pi over 4. So all I have to do is this. Integrate from 0 to pi over 4. of my function squared. Remember that r is the same as f of theta, just like y is the same as f of x. So don't let that throw you off. So all I need to do is square my function, put it in here. So it's going to be 8 sine 2 theta squared d theta, and that's it. Now, some of these, like I said, some of these you can integrate by hand. Some of them you'll integrate in the calculator. It's going to do this one in the calc. Now, here's one thing that I think causes some issues. We've been dealing with polar. Once you get this integral set up, you want to integrate it in just regular. You know, when you're trying to evaluate an integral with FNINT, you know, on this graph, if you go to second calc to try to calculate a lot of the stuff that you were able to calculate before, it won't do that. It'll let you do a few things. It'll let you find the slope at a point or something, but it won't do the stuff that we're used to being able to do. So get back into regular function mode. Then go to Math 9. That's my preferred way. And then just integrate this function like you normally would. And you're going to use x instead of theta, but that doesn't matter. The function that I'm integrating is 8 sine of 2x, close the sine, close the 8, square it. That's my function. I am integrating with respect to x, and I'm integrating from 0 to pi over 4. All right, so get back into rectangular. This is the integral. Divide it by 2, and you should get the area. So according to my formula, the area of one of those petals is about 12.5 square units. Just to kind of check it out, let's go back to mode, get back to my graph. I'm looking for about 12.5 units. My graph should still be in there. Try to just zoom in on it. Try this way. This method I'm getting ready to show you won't necessarily tell you that your answer is perfect, but it will eliminate some wrong answers. All right, so there's a good picture. And we're looking for 8.5 square units, correct? Or excuse me, 12.5 square units. Well, just kind of go and see what you've got in there. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It looks like I've got more than 12.5 square units. Let me pause and see what happened. Okay, I'm back, and I'm so glad that I was showing you how to check your answers, because you might have already seen what I did wrong. I changed my pi over 2 to a pi over 4. So let me switch that back to pi over 2. In my calculator, I change it to pi over 2. And basically, I get double the area that I have. So my integral was 50 when I divided it by 2 for the 1/2 out here. Then I got to 25. So back to where I was checking. In my polar mode, I should be looking for about 25 square units. So if I try that again, then, you know, you obviously can't get an exact number of units, but I knew from my last check that it wasn't 12, you know, so you can just kind of approximate. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, about 14, 15, 16, 17, 18. You know, you can count up the partial units, and I would have, if I could find exactly, I would find out that I have 25 point whatever units there. So that was definitely just a test to see. One more thing before we're done, make sure you're on the right day with these videos, because I've got a few ahead of time. So some people have watched the newest when that might not be the one that's for this day. So I'm not going to mention names, but it was Gifford. So with that, I'm out of here. Young out.